Dear friends, welcome to Lecture 7A. This is another approach to solve Ax equal to b, and while trying to do that, we find out the inverse of a matrix. So we will take a very different approach. We will not only stop at finding the upper triangular matrix, that is, we will not only stop at row reducing A to an upper triangular matrix U, but we would like to further row reduce A so that I get an identity matrix. So B would return to B tilde would be B bar. So the final equation would be Ix equal to B bar, where I is the identity matrix, giving me X equal to B bar. So automatically the B bar that I get on the right side would be my solution. So this reduces the operations that you are actually going to do with the upper triangular matrix. When you are going to solve that upper triangular matrix, that operation can be done automatically by row reducing U to the matrix I, that is identity matrix. Here of course we are all working with square matrices. If you don't have square matrices, things are slightly not so very interesting, so we will not get into that. So you see, let us look at this one. So the same old matrix, because this is good to take a fixed matrix and do a lot of games on it. So you are always already habituated with certain part of the calculation, so you can immediately understand what's happening. So you form the augmented matrix, and then you already know that U is this and B tilde is this. So can we reduce U to I? So again UB is now, so Ux equal to B is the equation. Now you are solving that part. You're further reducing I to U to the identity matrix, right? So here what you do to, so you take an augmented matrix of U and B tilde, which is this. So this will be B tilde, sorry. Actually B tilde becomes a new B, so it should be U B tilde. So what happens here is that this is, so the first I is here, here diagonal is 1, this diagonal has to be 1, this has to become 0, this has to become 0, right? This 3 has to go down to 0 and minus 1 has to go down to 0. So first I want to make this 1, so the whole row is divided by 1/3. So it becomes 1 here, here it becomes minus 1 on this side. Now what I want to do is, so I want to make this as 0. So what I do, I multiply the third row by minus 3 and add it with this. You can say, why I am not multiplying 3 with this row and add it with this, with the second row? Because then you will change this one, the diagonal. It will become, of course you can also do that, doesn't matter. 3 with this particular row, and then you can make this 0. Then again you have to add these two. So anything you can do. There are two different types of row operations you can do. One is that you can multiply with R1. I have suppose you can do it, multiply R1 with 3, so it will become 3 0 minus 1 0. So and then add it with R2 and replace it. So if you do it, so it will become 3 here, and that will be the problem. If you want to do it, it will become 3 here when you add that 3, you multiply by 3, and when you add it to this part, these 3 will go to 0, but a 3 will come here, and that will be a wrong thing. So you'll destroy the structure of the identity matrix. So the best thing is that what would happen if I multiply by minus 3 R3. So if I add it with anything in R2, I don't change these two, which is very important. This 0, not this diagonal. So once you do it, you multiply with minus 3 here and add it with 1. So minus 3 will give you here 3 plus 1 here, it will become 4, and then this will become 1 0 1. Now what you do, you just add, next step you add R3 and R1 and replace R1 with that, so it will become 1 0 0. You replace R3 now, minus 1 plus 0 is minus 1, it is this. So x bar equal to minus 1, 4 minus 1 is the solution. That's it. Now, this is a crucial thing that we have to keep in mind. Let us see what we did, right? Now, we are now going to extend this idea. This simple idea would be extended to look at how to find inverses. So what I did, I had the augmented matrix AB and I did a lot of row operations and I got I of x. Because x is the solution finally. Your B bar is actually your x. So this B finally is, through the row reduction, becomes my x. Because B bar is x, right? Because this is the solution, this is your x and this is your identity. That is what you have brought down AB to. So let us extend this idea intuitively to complete the inverse of a n cross n matrix A. So if a matrix A is invertible, then A inverse is a matrix such that A inverse is equal to I. So if I write A inverse equal to some matrix X, say capital X. So here I have an equation Ax equal to I, where Ax is playing the role of that small x, vector x. This matrix X is playing the role of that, and this I is playing the role of B. So A inverse or X, if I say, plays the role of X and I plays the role of B. So basically, from my intuition, let me do an augmented matrix. Instead of AB, I do AI. Now, when I have AX equal to I, so if A is invertible, then if I multiply A with X on both sides, what I will get? I will get Ix equal to X, right? Because X of A should be I, right? That's it. So X is the inverse basically. Capital X is the inverse. I have written A inverse equal to X. So we have now done the augmented matrix. Now our job now is to do a row operation on them, and just extending this intuition. Instead of thinking of B as a vector, think of it as a matrix. Instead of thinking of X as a vector, think of it as a matrix. And once you do, you extend your imagination. And once you extend the imagination, you can immediately say that I can reduce this A augmented I to I augmented X, where X is the matrix. So if I do a row operation on this, when I is on the left side, A is transformed to I and I would be transformed to the inverse of A. That's fantastic. That's intuitively, it looks fantastic. So can we give it some rigor? That's the idea. So let's take a 3 by 3 invertible matrix, and X is the inverse, and let X has these rows, these sorted columns, X1, X2, X3. And let I has these 3 columns, E1, E2, E3, where E is I 0, 0, E2 0, 0, 0, 0, 1, 0, E3 is 0, 0, 1. You must ask me, why are you just doing it with 3 by 3? So 3 by 3 is easy to explain. Otherwise, of course, I can do it with n, but everybody may not immediately grasp the abstraction. So idea is to allow people who may not be so fast in grasping abstractions to actually think of it, right, in a simpler way. So what is happening when I am writing A of x equal to I? If this is the equation, then what does it mean? A of x1 must be equal to E1, A of x2 must be equal to E2, A of x3 must be equal to E3. So x1 must be equal to A1, assuming that A is invertible, A inverse E1, which is xE1, x2 is A inverse E2, which is xE2, x3 is A inverse E3, which is xE3. Okay. So now what is happening? For any of these i's, I1, 2, 3, whatever, if I want to solve this equation, what I do? I have A augmented EI row operations will give me IXI. Obviously, x1, the vector. So first row of the inverse actually. So if I now write E1, E2, E3, augment these two columns also and then do the row operations, I'll get I, Xi, X2, X3 because I will change. Right? Oh, you might ask, okay, here you are doing a different row operation, here you are doing a different row operations. But what would happen is that finally you can, what are you going to do? If you, basically if you're doing the row operations on the individual, A inverse x1 equal to E1, A inverse x2 equal to E2, A inverse x3 equal to E3 and solve them out, then also you get x, you directly get the x vector. So what one can do is that augment this whole matrix now. So you have this row operations. You have done this row operations to get IXI. On A, the row operations will not change. To make A to I, it does not matter how many E1, E2, E3 will be there. Suppose it could be a n cross n matrix. There will be E1, E2, E3, En. So for each of those EIs, to convert A to I, there's only some fixed row operations. It doesn't, you might feel, okay, will it change from this equation to this equation? No, it doesn't. For A, it doesn't. But for E1, so for whatever you apply for A, the same row operation you will apply here to get A to I, the same row operation you apply on E1. The same row operation you will apply to make A to I here, you get E2. The same row operation you apply on A here to get E3. So they fear that, okay, row operation might change from one position to another is misnomer, because to get A to I, there is only some fixed row operation. So that all the fixed row operations are also acting on E1, E2, E3. So if you just make an augmented matrix with having all these rows, so getting this identity matrix here, right? And then doing the row operations, you will get I on this side and you will get x1, x2, x3 on this side, because you will be essentially solving out each of them individually, and that will be A inverse. So that's what it is. So let us again take a look through the same matrix again. So here I have done AI. So I am trying to convert I'm doing an operation minus 3R1 plus R2. So making this 0 first. And then again I'm going to the U finally. So I have done minus R1 plus R3. And I'm doing R2 plus R3, which you know already. So this side is changing, you see. And then I am doing this 1/3 of R3, and then all this operation that you have just seen just before, to bringing the whole thing to I, minus R3 plus R2, which is this, plus, so this side is also changing when you are doing these operations. So again R1 is changed with R3 plus R1, right? So if you add these two, R3 plus R1, and change it, this will become 0. That is the last one you have, when you have seen in the last, just the section ahead, we had discussed this. So A inverse, which is X here, is nothing but this matrix. So that's it. That's so beautiful. So we have written here, we'll end our discussion here, but we will not end our discussion here. Instead, we are going to now talk a bit about the algorithm which I had written down myself, just trying to think about while writing the notes. I just wrote down the algorithms. So how do we do this Gaussian elimination? Can an algorithm develop it when I do it? Because in general for big matrices you are not supposed to do it by hand, there has to be a machine. So you start by initialization. I equal to 1 means you are taking the first row, right? So I equal to 1, I 1, 2, 3, 4, 5, 6, 7, 8. Right. If I is equal to 1, then you have to now eliminate. So if I is equal to 1, starting from k is equal to 2 to n, that is a21, a31, an1, you have to eliminate all the column elements and make them 0. So what happens when I is equal to j, when I am in the jth element or jth column and jth row, I am in the jj position of the diagonal. So anything below, so in the jth column, from j plus 1 till the nth position, all those elements have to be thrown away to 0. So when I come to a position j, jth column or jth row, so I am in the jth row, jth position column. So I am in the diagonal element. So after the diagonal element on the column, there is element in the jth plus 1 position to jth plus 2th position to nth position. So what I have to do? I have to set, as we have seen earlier, minus akj by ajj's, because here if you look at it, if you want to do your very first operation, so here is a matrix, 3 by 3 matrix for example, and then you want to reduce this out, take this off to 0, and what I do, I multiply the identity matrix by, so the first row of the identity matrix by minus L and add it to the second row and replace the second row by this. And we want to know what L value should be so that A21 would actually reduce to 0. So what I do, write this A as A1, A2, A3, and then I will multiply E21, this elementary matrix, with A. So what I do, I separately E21, I do it with A1, this first column. So that has to be affected, right? That will be affected. So if you look at it, I immediately get, if you do the multiplication, the second element is A21 minus LA1. This is what you want to become 0. You want this to be 0. The next part, so actually we want this to be 0. So L is equal to A21 by A11. So my elementary matrix that I have to choose is, here J is equal to 1. So J plus 1 is equal to 2, right? So you have to take A, if J is equal to 1, then you have to take J plus 1 by, here you have taken A11. A11 means this one. So if I have AJJ, I should take this to be AJJ. And here, what did I do? What was this position? This position was, so LK it would be something like. So it would be AK plus 1J by AJJ. So when you start from that position. So let us go back to the algorithm. Let me see if I have done it right. So K is equal to J plus 1 to N. So for K equal to J plus 1 to N, you will set L equal to this. So for the first row, you are multiplying. So K equal to J plus 1 to N. So AKJ by AJJ, A2 1 by A3 1 minus A2 1, A3 1 by AJJ. This is what would be the value of L, right? So construct EKJ from I with kjth element 0 replaced by minus L, because kjth element in I can never be 1, it is always 0. Only the jjth element is, or kkth element is 1, right? So that is replaced by minus L, right? So that is replaced by when L equal to something. So minus L. So L would be not minus, it will be plus, sorry. So it will be plus here, plus AKJ by AJJ. That is a mistake here. It should be plus AKJ by AJJ. So you compute for first K. So this is for a fixed J now. J is fixed. Now you are looking at the first position, J plus 1. So you do for E, K, J plus 1, J, A. You do this computation. Now assign the new matrix A now becomes the matrix EKJJ. Then update K to K plus 1. Now J plus 1 will become J plus 2 and again do the same operation till you reach N. So when K is equal to N, you have ENJ. A is again assigned to A, and now you set J, this J to J plus 1. So now I would be now equal to J plus 1. And now you will have to come to the position, diagonal position, J plus 1, J plus 1, right? So you now come to the diagonal position J plus 1, J plus 1. Okay? Maybe the writing has to be improved a bit. You can do it yourself. So now and again go back to step 2. Sorry, step 1, not step 2. Step 2 is here. This is go back to step 1. So you go back to this step and again do. Now here I is J plus 1. Now for K equal to J plus 2 to N, you have to carry out this operation. So it will become A J plus 1 J plus 1, A K J plus 1. A is equal to this plus, not minus. And again you start doing A K. Instead of J here, you will have A K J plus 1 from I to I with K J plus 1th element, and do the, they keep on doing the same thing. Basically, right? So that basically you have now J, you have assigned J to J plus 1. And J plus 1 takes the new value of J is J plus 1, and you start again the whole operation. Repeat it. So how long you have to repeat it? For start with I equal to 1, 2, 3, 4. I equal to 1, I equal to 2, I equal to 3. When I start with and for this step you will stop. When will you stop this step? You will stop this step when you have covered every one. Start with I equal to 1. So when I is equal to stop when I is equal to N. When the computations of I equal to N is over, stop it. So that would be giving you the upper triangular matrix. I hope this is very, see what you are doing, applying. If you have seen what we have done earlier, we have applied the elementary matrix from the left, multiplied it, got the new matrix, and this new matrix now behaves like as if it is A. And now we will do operations on this new matrix. So that is what is given you. So for L here it is a plus, not a minus, and then it's the same operation. You see this EKJ now becomes the new A, and then we do the same operation. Okay, thank you very much. Hope you have enjoyed this little talk and have fun. Bye bye and good night.